Hello and welcome to Bay College's Intermediate Algebra online lectures. Today we are finishing section 1.7. This is the third of 3 videos, and we're going to talk about absolute value inequalities. The first 2 videos dealt with intersections and unions, and now when we work with absolute value inequalities, it actually ties those 2 concepts together. So the first thing we're going to look at is the absolute value less than 6, because now we have an absolute value, and if we recall from the very first video of the lecture series, we dealt with absolute value equations. Well, absolute values just ask us, what is a distance? They're asking for a distance, and we know distances are always positive, but here it's asking us, we want to find distances that are less than, greater than or equal to, less than or equal to. So they're dealing with inequalities. So in this example, it says the absolute value of x is less than 6. Less than 6. We want distances that are less than 6. Well, if we recall an absolute value equation, we're saying how far from 0? Well, 6 to the right is positive. 6 to the left is negative. But the distance is an absolute value. It is positive units. But now that it's an inequality, we're saying what distance is less than that. So to be less, we're saying between 0 and 6. These values are less distance than 6. And on the left of 0, same thing. From negative 6 to 0, the distances are less than 6. And if we recall, this looks just like an intersection. Less than, when dealing with absolute values, is asking us just that. It's an and statement. It is an intersection. And intersections can be written as a double inequality. So for our set notation, we're going to use a double inequality. And we could just take that from our graph here. We have from negative 6 is less than x is less than 6. And I kind of skipped a step because we recall when dealing with absolute value equations, we can always write 2 equations. This is a way to algebraically think about it. We can have x is less than 6. That's our value to the right. And we could have x and negative 6, our 2 equations. But because this is an inequality, if I change the sign of the number, I have to remember to change the sign of the number. And essentially, that's what this graph says. Less than 6, but greater than negative 6. The area in between here where they overlap is our intersection. And if we think about it this way, x is less than 6, well, that's just this piece of the set notation. X greater than negative 6, if I could lift this off the board and turn it around, it would tell me this right here. So I just put the 2 together. Now, in interval notation, because I use the parentheses on my graph, I can simply just transfer this information. A parenthesis at negative 6 and a parenthesis at positive 6. This is the interval of solutions to this absolute value inequality. Less than asks us to go looking for the intersection. What solutions of the 2 possibilities hold true in both of these equations? And it's always important to check your work. Let's choose 0 since it's in this interval. Is 0 less than 6? It absolutely is. Is 0 greater than negative 6? It sure is. So we know that the values within this area is true and holds true for any value in that area. So let's look at an example here. We have the absolute value of x plus 7 is less than or equal to 3. Well, one good thing is we have our absolute value already isolated to one side, just like we did with equations. So we don't have to worry about that. But just like an equation, we want to write 2 equations when it comes to these inequalities. One could be x plus 7 is less than or equal to 3, the positive value, or to the right of 0. And the other, and because this is a less than, it is an and statement. The other equation is x plus 7 is greater than or equal to negative 3. Because I changed the sign, I need to change the sign. Redundant statement, but infallible. So now we're just going to solve it using our properties of equality, but in this case, inequality. I'm going to subtract a 7 from both sides and I get x is less than or equal to negative 4. Here I'm going to subtract a 7 from both sides, and I get x is greater than or equal to negative 10. Now, this is my set notation, but it's not in proper set notation because we can write it as a double inequality. So I'm just going to put it in order from least to greatest. And I know that negative 10 is less than or equal to x, because x is greater than or equal to negative 10. And x is less than or equal to negative 4. So we've also written it in set notation, proper set notation. We can graph this quantity. If this is negative 10 and this is negative 4, the intersection here is in between negative 10 and 4. Now notice I used brackets here because these are equal to symbols. So these brackets tell me I do include these end values. And now I can write my interval notation simply by pulling it off the graph, negative 10 to negative 4, including these endpoints. All right, we're going to look at another example. I'm going to erase this. If you need to see it again, this is a wonderful thing about technology and videos. You can just move that cursor bar and back up in time and watch it again if you need to. My eraser's over here. All right, our next example, notice that our absolute value is not isolated. So that's the first thing we need to do. We need to add 5 to both sides. Negative 5, we're going to add 5 to both sides. So I get the absolute value of 2a is less than 4. Less than tells me look for an intersection, an and statement, the values, the distances that are less than 4. So now I can write two equations or two inequalities. 2a could be less than 4, and 2a could be greater than negative 4. Always remember, when you change the sign, to change the sign. And we can solve both of these simply by dividing each side by 2. So I get a is less than 2. And here I get a is greater than negative 2. Let's go ahead and graph this, because many of our instructors in our 105 classes are going to ask you to write it or graph it, write it in set notation and interval notation. So we need to know how to represent our answer in every possible way. So this value here says a is less than 2. And that would be this area. A is greater than negative 2. That would be this area. And we can see definitely looks like an intersection. That's good news. In interval notation, since it does not include our endpoints, we use parentheses. And set notation, we're just going to recopy these in least to greatest order. Negative 2 is less than a is less than positive 2. So we found that solution. The only way this was different than the previous example is the first step is we had to isolate the absolute value. Now we're going to look at this example right here. And I'm hoping that with enough practice, we'll be able to look at this and say, hey, there's something here that's different than the others. And maybe we can intuitively say, you know what? This has no solution. Because if we truly understand absolute values, we know absolute values are always positive. Is there any time when an absolute value or a positive number is going to be less than a negative? Positive numbers are always greater than negative. So this is not a true statement because this is always positive. So if we see that, we can say, you know what? There is no solution. So we can use the null set, or we can actually write out no solution. Again, I love to abbreviate because my spelling isn't very strong. All right, but what if we don't recognize this? Maybe we can write our two equations. Well, what if I say 2a minus 5 could be less than negative 1. I didn't change any signs, so no need to change any signs. And I say 2a minus 5 could be greater than positive 1. So I changed it up a little bit. Well, I'm going to go through and solve it because I didn't recognize that there was no solution. I'm going to add 5 to both sides. and I get 2a is less than 4. I'm going to divide by 2, and I get a is less than 2. Here, if I add 5 to both sides, I get 2a is greater than 6. Divide by 2, I get a is greater than 3. Now, if I try to write this in double inequality form, because it is a less than symbol, it says and find the intersection. Well, I have my smaller value 2, but 2 is greater than a, which means a is less than 2. 2 is greater than a. And here, a is greater than 3. Well, if we just stop for a moment and cover this up, 2 is greater than 3. That does not make a true statement. So this cannot be right. Even though it is these quantities, it doesn't make a true statement. That's another sign. We should say, you know what? If I were to choose a value between 2 and 3, let's say 2.5, doesn't make a true statement. Let's plug it back in here. 2.5 times 2 is 5. 5 minus 5 is 0. 0 is not less than -1. So that's not a true statement. So that tells me right there there's something fundamentally wrong. If I tried to graph this, I would see on my graph, if this is 2 and this is 3, a is less than 2. Well, that's this value over here. A is greater than 3. That's this value over here. That kind of looks like a union, doesn't it, as we discussed in the previous video? Well, we're not going to find an intersection if these don't overlap. Less than told me to find an intersection. So that's not the case here. So if we check our work and continue to check our work in every case, we're going to come to the right answer. We're going to say it has to be no solution. All right. So we've seen our less than symbols and how they apply to intersections. Well, the inverse is true for greater than symbols. They're not intersections. They are actually or statements, or what we call unions. So if we look at this example, the only thing different than our first example is that we changed the sign to a greater than symbol. So we're saying, what are the distances that are greater than this value, further away from 0? If we go ahead and graph this, if this is -6, because we're dealing with the absolute value, we can have two possibilities. X could be greater than 6, or x could be less than -6. We change the signs when we change the signs. So if we read this statement, x is less than -6, that brings me to all the values to the left of -6, further down the negative trail there. And the other one says x is greater than 6. This looks just like a union. Now, the thing about unions is they cannot be written as double inequalities. So what we have to do is we have to write it using this value set notation, but we throw in that or statement. Because we could have x is less than -6, or x is greater than 6. This is the union. We're uniting these two separate intervals. All right, and to write that in interval notation, well, if we look at this piece of our graph, it goes from -infinity to -6, does not include -6. And we unite it, use the union symbol, from 6 to positive infinity. So that we have our graph, we have set notation, and recall that unions cannot be written as double inequalities, so we have to introduce that or statement. And then our intervals, hopefully we're all familiar with interval notation at this point in algebra. So let's look at an example of a greater than absolute value here. We have the absolute value of a plus 1 is greater than 4. Well, since our absolute value is already isolated, we're going to write two equations. A plus 1 could be greater than 4. No need to change any signs. Or, and I use the or statement, a plus 1 could be less than -4. So we use an or statement. We're changing the sign because initially it was greater than, the distance further away from 0. And we solve that. Subtract 1 from both sides. We get a is greater than 3. subtract 1 from both sides, we get a is less than negative 5. If we are to graph this, and I'll just graph it right here, we have negative 5 on the left, 3 on the right. The statement of a is greater than 3 says, let's go to the right, but we're not including it, so we use a parenthesis. Here it says a is less than negative 5. That's to the right. And now we can write the interval. Where does that arrow go to? Negative infinity. As we move to the right, we get to negative 5. Does not include it. We use the union symbol because it's an or statement, a union. We start at 3, but not including. And this arrow continues on for infinity. So the 3 ways to represent our answer, we have our set notation, we have our graphical representation, and we have our interval notation. Now, depending on what you're asked to do on an assignment, whether you're asked to do it in set notation, otherwise known as algebraic notation, graph notation, interval notation, you should be familiar with all 3 ways to represent your answer. All right, let's look at another example. Similar, but slightly different. Have to clear a little bit more board space here. Again, if you do miss anything, you can always rewind your tape. That's old technology, right? Digital video age, we don't rewind anything. No need to be kind anymore. All right, we look at this absolute value. First thing we have to do is isolate the absolute value. The first one that we did, it was already isolated. Here we have to isolate. I'm going to add 9 to both sides. The absolute value of 2x is greater than or equal to, when I add 9, I get 4. Well, now I'm ready to write my 2 inequalities. 2x could be greater than or equal to 4, or 2x could be less than or equal to negative 4. Always remember to change those signs. Now we divide by our 2, and we get x is greater than or equal to 2. Or divide by 2, x is less than or equal to negative 2. Now, by doing it this way and introducing that or statement, it is already in set notation, but we should have the lesser value on the other side. So we could switch it, but for time's sake, we'll accept this right here. We're going to graph this. Here's negative 2. Here's positive 2. Now, this statement here says x is greater than or equal to 2. So the positive 2, it says greater than. We're going to go to the right. X is less than or equal to negative 2. Less than, we're going to go to the left. And we can see, yep, that sure looks like a union. Let's unite them in our interval notation. Negative infinity to negative 2, but we're including negative 2 because of this equal sign. Union to infinity. And again, we use that bracket to indicate this value is included. So we have our 3 representations of the answer. And one thing I didn't do in the previous example, but I will do in this example, check our work. We should be checking our work. If I choose a value in this area here, it should solve one or the other. And that's the key to a union, that or statement. So let's try negative 3. Is negative 3 greater than or equal to 2? No. But is it less than or equal to negative 2? Yes. So it solves one or the other, in this case, the other. If I choose a value in here, 3, 3 is greater than or equal to 2, but it's not less than or equal to negative 2. So it solves one or the other. Now, to really check it, it's always good to check your work. We can choose a value that's not in this interval. Because it's not in either of these intervals, it should not solve either of them. This is not the area of solution. And we check it. Is 0 greater than or equal to 2? No. Is 0 less than or equal to negative 2? No. So this area here doesn't solve one or the other. It solves neither. So this is not the solution. And that's why this union excludes that area. All right, let's move on to our last example. And then we'll do a little summary of the last 3 videos that we've covered. Here we have the absolute value of 2x minus 9 is greater than negative 5. Well, hopefully we see this again, just like in the previous example when we had less than a negative. Here we have greater than a negative. Well, when we had a less than symbol, the intersection did not exist. Well, here, if we realize the absolute value is always positive, when is a positive value greater than a negative value? Always. Positives are always greater than negatives. So in this case, when we have that greater than, if we intuitively see this and say, hey, I've worked with absolute values long enough to say absolute values are always positive, positives are greater than negatives, we can say this right here, this is all real numbers. This is the symbol we use. Or we can write it in interval notation, negative infinity to infinity. That includes all the real numbers. Graphing this essentially is the number line. Because it includes the entire number line, it is the entire number line. So there's really no need to graph it. Okay? So what if I did not recognize this? And that's going to happen. You know, when we're first starting out in algebra, it's the practice that gets us to where we need to go. So when we're first starting out, maybe we write these two equations. 2x minus 5 is greater than negative 5. Didn't change any signs. 2x minus 5 is less than negative 5. And I apologize for crowding it into the board. I'll move over this way a little bit. If I add 5 to both sides, I get 2x is greater than 0. And here, if I add 5 to both sides, I get 2x is less than 0. Oh, you know what? I forgot to change the sign. This would be 10. I'm adding 5 there. So remember, when you change the signs, right? Even your instructors make mistakes. All right, x is greater than 0 if we divide both sides by 2. And here, divide both sides by 2, we get x is less than 5. Well, let's go ahead and graph this and see what actually happens here. X is greater than 0. Well, if this is 0, x is greater than 0. And 5 somewhere over here, x is less than 5. That's this area over there. And if we look at these two arrows encompass the entire number line. They do have an area of overlap. It looks like an intersection, but we have to remember this greater than is asking us to find the union. It's an or statement. So if I want to include all the solution, what solves one or the other? Well, according to this, the entire number line will solve one or the other. So our answer is all real. So that brings us right back to here once we graph it. But we got to keep in mind, am I dealing with an or statement or an and statement? Always check that to say, is it all real or is it no solution? The symbol is what's going to lead you to that conclusion. All right, lastly, we're going to summarize the last 3 videos. In the first video, we talked about unions. And then the second video, we talked about, in the first video, we actually talked about the intersections. Then we talked about unions in the second video, and now we tied them together by introducing the absolute values. So when we first discussed absolute values in section 1.4, we know that if we have an absolute value equation, we're going to get 2 solutions, to the left of 0, to the right of 0. So x would equal plus or minus a in this example here. Now, when we introduce an inequality less than, well, we can write those as double inequalities because they are intersections. We're actually looking for this area in between negative a and a for the absolute value less than a. And that is an intersection, and we remember those are and statements. So if we have absolute values greater than a number, we're actually looking for or statements. And those or statements are x could be less than negative a to the left, or x could be greater than positive a to the right of that value, leaving that gap in the middle like we have here. There is no intersection because we're looking for a union, an or statement. So if we just keep these concepts in mind when dealing with the absolute values, we can see that less than are intersections and greater than absolute values are unions. That concludes section 1.7 notes. Thank you for watching.